Hi everybody, thank you for coming here. And right now I'd like to talk a little bit about Project Loom and particularly about Java virtual threads. And just a short slide about myself. It's not my job titles, it's just what I was doing for a long time. I was working on Java performance, and of course here I'll try to talk a little bit about Loom performance. So right now for JDK 20 we prepared 3 different jobs which are made under umbrella of Project Loom. It's a virtual thread, structured concurrency, which survives the second JDK. Both these jobs were in JDK 19. And the third job for scoped values. Okay, let's talk about virtual threads. It's the key goal, the key feature of Project Loom. Virtual threads are user mode threads that are lightweight enough so a single Java process could have hundreds, thousands, and millions of them running concurrently. The purpose of virtual threads is to allow to Java developers to create high effective, high throughput servers. First of all, it's targeted for server applications, and at the same moment to allow people, developers, write a code in a simple thread per request style and don't deal with different kind of asynchronous programming. And of course, I have to warn you, it's not a final, it's everything that we did for Project Loom. It's a preview API. It's maybe changed a little bit in the future. It could be extended in the future. And of course, you can find bugs here. But anyway, your feedback is quite important. That is why we made it as a feature preview. Even before then, we finalized everything. Before talking about what's done in the Project Loom, a short talk about threads. Initially, it was created like Java threads on the top of operating system threads, and there are no such place in Java specification and any other Java place where we have some limitation for threads. Thread in an abstraction, it's a nice and useful construct for concurrent programming. But eventually, our implementation came to the fact that each Java thread is just a simple wrapper over operating system threads. And here, finally, we've got an issue. Because of operating system threads, they're expensive. We can't have millions of operating system threads. Typical the number which allows to work is 1,000, 10,000, but quite rarely more. It's a natural behavior of operating system threads. And it became that from one point of view, we have just an abstraction, just a construct for concurrent programming. From the other point of view, it became a resource because of it's expensive. And somehow we have to deal with that. How to deal with these? Just an example of how thread is expensive. If you take our Java microbenchmark harness functions, black hole consume CPU, which does almost nothing, just a little bit. And if you run it sequentially, it takes, as you can see here, quite a small amount of time. If you try to execute it in Java threads, doing fork and join, waiting until all computation will be done, it will require much, much more time. A very, very large amount of time is required. So the community, the people around, its solution was found. If threads are expensive, we need a smaller unit of concurrency. And that leads to asynchronous programming. There are a lot of kinds of different asynchronous programming in different languages, and etc., etc. But unfortunately, asynchronous programming has some issues. First of all, it's viral. You have to rewrite the whole program to asynchronous programming style. you're losing observability, troubleshooting, debugging, profiling. And concurrent reasoning is hard even with threads, but having larger, more vast amount of our concurrent units, we became it more harder. So, and if we would like to make another language from scratch, like Kotlin, maybe it could be avoided. But Java, it's made of threads. And everything in Java is threads. We have exceptions, and we have stack exceptions. We have thread local variables. All debuggers, profile, everything is working with threads, and it creates really difficult to program, to require more efforts to develop fast enough performant asynchronous programs. And there is a dilemma, what to choose: convenient, fast, easy to way, synchronous way with a blocking API. When developers are happy, but our hardware much less utilized, we can provide enough utilization for our hardware. Or to use more performant asynchronous programming, but it's more difficult to develop and require more efforts. What is the better? So the Project Loom provides the second way to solve the issue with thread expensiveness. We are giving the second way. We are trying to make threads cheaper. So what is a virtual thread? First of all, it's a thread. It's the same thread as before. So you need no care about some other details. And because of it, lightweight threads, Java threads, Java runtime knows how to deal with those threads much better than operating system does, and provide it more efficiently. We have realizable stacks, we have context switching in user mode, and we have, of course, our internal scheduler. The very nice feature of virtual threads is that no need to rewrite the whole code if you want to use it. It's not a synchronous style of programming when we have to do a lot of modification. At the same, we didn't change, we don't change, and we won't change the behavior of classic Java threads. In order to distinguish it from virtual threads, we call such threads as platform threads. The behavior of platform threads remains the same as now, because there are huge vast of frameworks on other things in Java infrastructure which relies on such behavior. And just a simple picture how it works right now. We have still one-to-one mapping between platform threads and operating system threads, and we have virtual threads which are mapped to execution on some subset of platform threads which called carrier threads, and performing that. Also, we have our own scheduler which schedules virtual threads. And right now, with virtual threads, we are getting ability to make both programmer and hardware happy. Using virtual threads is quite simple. First of all, we created a new object thread builder. You may build thread, tells that we are building a virtual thread, and execute it as a usual classic thread before. The second way is we have an executor which manages execution of all tasks inside this executor with virtual threads. It's two simple ways. A little bit about performance. Most of that examples is not relevant, it's just a small micro benchmark, but they will show you the difference in behavior. Let's check what will happen with our do nothing 1,000 times micro benchmark. Again, it's the benchmark when we run concurrently 1,000 tasks and wait until all of them will finish. How much time we require to get the whole results. And here we can see that virtual threads are much better than platform threads, but of course there is some competition with asynchronous programming. Anyway, classical platform threads are too expensive in this way. Let's another example. Let's do nothing, but not for a short amount of time, but do nothing for a long period of time. When our thread just spend time in its thread sleep for 1 millisecond. And here we have another results. And this is results where even platform threads outperform asynchronous programming, but virtual threads are much better. Of course, we should check our behavior on CPU-intensive tasks when we do some CPU computations. This particular CPU-intensive task for 1 millisecond. Here, the results may vary, but definitely, if you will switch to practical applications, I'd like to say that you won't see any difference for CPU-intensive tasks between platform threads, virtual threads, and asynchronous programming. It works almost in the same way. And where we provide a better performance for this, it's of course I/O. I have short examples, numbers for when we read a file from a file system on my. These numbers are got on my laptop, and we just count MD5 hash code for this file. For small file, it even doesn't make sense to do any parallelization based on platform threads in comparison with sequential execution. It works quite fast, and virtual threads and asynchronous programming works even better. Middle-sized file. Just here, we finally got some benefits from parallelization, but again, virtual threads and asynchronous programming provide a much better performance for file and a little bit larger file. Just, I think these numbers quite obvious. But all of that, it were just artificial examples, micro benchmarks. It's not real application. Here's a real application which was mentioned in a previous presentation. It's a Helidon NEMA. It's a web framework, and it's written in a simple style thread per request. All API in that application is a blocking API, and we quickly achieved the performance comparable with well-known and perfectly tuned other web frameworks which incorporates asynchronous programming inside. Here on the chart is a throughput, then higher bar and the better. We had one presentation about Helidon here, and we will have hands-ons about Helidon. You may ask many questions. I'd like to tell you a little bit about my personal practical experience with Helidon. As a performance engineer, several years ago, I was working on a new HTTP client, which was implemented in GTK 11. It's a new HTTP client which supports also HTTP2 protocol, and this client was written allow you to use two kinds of programming: blocking API and asynchronous API based on Java util concurrent completable future. I was working on that project. Also, I looked into Helidon NEMA source code and check how it works, provide some measurements, maybe ideas for optimization, etc. And from one point of view, it's quite a different framework, different set of API. From one side, it's client. From other side, it's web server framework. But they have a lot of in common. For example, processing HTTP2 protocol from both sides look like the same. And I have to say that in Helidon NEMA, the code which process different kind of HTTP, HTTP 1.1, HTTP 2. First of all, it's much simpler. It's a straightforward blocking API in a thread per request style. It's much simpler, it much less in size. The number of files, first of all, I downloaded Nima, I looked into code, and my impressions. So a few files, so a few lines of code, doing the same as we did before for asynchronous in HTTP client. Maybe it's not implemented yet, but at the end I realized that it was fully implemented and provides much more efficiency for developers how to deal with that. Because of, anyway, sequential programming we understand much better and we work with that much faster. And some examples about performance and a lot of things, it's around a Little's law. Little's law, it's one of fundamental laws in queue theory and provides, it has a vastly usage in performance, etc. That law, it means that the production of latency of requests and the throughput of our system equals to the number of concurrent requests. It could be just a number of queue, it could be a parallel concurrent number of requests on flight. And there are two key things about that law. First of all, that law works for a stable system. It doesn't work for systems where size of the queue is growing, etc. And the second important fact that law does not depend on any statistical distribution on incoming requests. That allows to use it. And example how to use it. Let's say we have some restricted resource in our system. And it's our first bottleneck, our first resource. We don't meet any other bottlenecks before we stuck into that. And the number of concurrency for that resource is 30. It could be just 30 cores for our application. It could be limit of connections to databases is 30. Just an example. And the time which we utilize this resource is 100 microseconds. We do some request, we do it for 100 microseconds. According to Little's law, the theoretical maximum available throughput when we meet that bottleneck is 300,000 requests per second. Simple computation. Okay, let's move further. If we are dealing with that resource and we want to achieve our high theoretical throughput limited by this bottleneck by 300,000 requests per second, and the overall time of the request is, in average, is 50 milliseconds, it means we need concurrency equals to 15,000. It means we need, for thread per request style of programming, we need 50,000 threads. That's a lot. It's really a lot, and not frequently we can achieve it. Because of its classical operating system thread is a resource. And here is examples. It's a slide which also you can saw on the previous talk. It shows a Little law in actions. It's a practical results which were made for Jetty server when simulate request for 100 milliseconds with some I/O limitations. And exactly according to previous formula of Little's law, you can see that if we set up thread pool for 200 platform threads, we quietly reach our throughput around 2000. If we set up 800 platform threads, we also reach the same maximum available throughput as predicted by Little's law. And using virtual threads, we don't met any limitation by our threads, but number of our operating system threads, and we'll provide higher and higher throughput until we really met the real bottleneck in the future. It's quite important, and a lot of question about is how to move your application to virtual threads. And the first and most important idea that don't write asynchronous code. Use the simple, old-style, non-fashioned, boring, single-threaded code, catching exceptions as usually are doing. It's the better way. And the fact is, the real power of virtual threads is their number. You can't achieve efficiency of Project Loom just convert 100 virtual threads into convert 100 platform threads into 100 virtual threads. You need thousands or probably millions of virtual threads. Virtual thread will provide benefits only if you have a lot of them. You should convert your task, not a previously thread, into virtual thread. So, virtual threads are not resource now. It's just a logic. It's a business logic, or you may consider it a language construct which allows you to make a concurrent programming. You should not care about virtual threads as before. And of course, you should not pull virtual threads. It doesn't make sense completely. Virtual threads are designed to just do their work and die after that. Thread pools of classical thread pools everywhere, they use not only for reusing threads, don't avoid that expensive creation and eliminations of our objects, but a widely used technique, it's a limiting concurrency. It's a frequent task when we have to limit concurrency of our application by some reasons. And size of threads pool is a normal and classical way to do it right now. You shouldn't do it for virtual threads. Just use semaphores. It's another concurrent construct which is designed especially for limiting concurrency of your application. Don't pull virtual threads at all. Oops, I missed it. The second problem is thread localhost objects. Thread local objects, they are created for threads, they are accessed only by single threads, and usually they have two kinds of different usages. First and widely used scenario is using thread locals as a hidden parameters for our functions, actions, and everything we are doing within the single threads. We made scoped values for it. I won't talk about scope values today, it's just a preview, but it's a new technique, it's immutable objects which allows for you to interchange any information and data. The second usage of thread locals, which was not intended at the beginning of thread locals design, but widely used in the code around the world right now in Java, it's local caches. We want to cache some expensive objects or objects which we think they're expensive, and we put it into thread locals to provide locality and fast access. Don't do that virtual threads. Virtual threads have a short period of time. We have millions in virtual threads, and using thread locals, it's a really, really bad idea. I observed some experiments where highly effective throughput-oriented applications, server-side applications, with adding thread locals into virtual threads, not platform threads, that application got 20% slowdown in throughput. It's probably should be avoided. And the other problem for virtual threads is pinning. We call difference process inside. When virtual threads start executing on carrier threads, this process is called mount. When virtual threads removed from execution to some pool of waitings, virtual threads is called unmount. But sometimes Java runtime can do that unmount action. Right now, there are two sources of pinning. We we pinned that virtual thread for our platform threads and eventually to operating system threads. And because of we can't move that virtual thread from execution to unmounted, it's pinned to our thread, and that virtual thread, for example, blocked or waste resources. We are wasting our virtual threads, we are wasting our Java threads, and we are wasting our operating system thread. And there are two sources of this. First of all, not mentioned on that slide, it's a native. If you have native parts of your code and you from the native code you jump to Java, and in Java you want to release virtual thread, that thread will be pinned for execution forever. We can't remove it. We have native frames on the stack above, and we can do nothing with that. The second source of pinning is a native synchronization or synchronized on monitors. Java has two ways of synchronization. It's from the beginning, it's keyword synchronized and monitor stated with every object. And that technique exists since Java 1.0. And a later technique, it's the whole package Java util concurrent logs, which appeared in Java 1.5 many years ago, which also provides a more flexible and more powerful way for monitors. And right now, currently, for current stack, we implemented Project Loom virtual thread only for Java util concurrent logs, log friendly. These logs are Loom friendly, and if you're blocked on some monitor, that virtual thread will be removed. Unfortunately, it's not implemented yet. In case of synchronized work, it will be pinned and not removed from execution. It's a temporal state. We are working on implementing classical synchronization on object monitors fully Loom friendly. Please wait next updates. And even right now, for this, we provide some tracing abilities. You may use GFR, or you may provide property GDK trace pin threads and check when threads were pinned and to avoid it. I'd like to do a little bit warning about total and pervasive migration from synchronized object monitors to Java util concurrent logs package. It doesn't require, it's not necessary to do it every time. You should move from synchronized monitors, native monitors, to reentrant logs only if this block of code doing long I/O operations. If it's just a simple block around some state machine, when we have 5 variables describing state of your computations, you have to synchronize it to make it work correctly. But it's just a small set of changes for memory modification, and from performance point of view, it's not required to move it to new concurrency. And here is a simple short limitation. That's all about virtual threads. We did a lot of optimization inside, how it works. It's probably ahead of topic of this presentation. So if you have questions, we could discuss it. I want to say a couple words about the second JEP. Second hour JEP, it's about structured concurrency, which is still in incubator. What we have right now? Right now we have two kind of ideas, kind of action, how to write code. We may write classical, ordinary, sequential code, which simple, which provide failure propagations, I mean exception, of course. If something failed, you may just throw exception out of there, and it's efficient. But it's sequential. And we have a concurrent code, which is completely unstructured, failures not propagated, very difficult to understand where we have a source of that exceptions, no short-circuiting things, and etc. And of course, it's everything. This is not stack-friendly, not very good for observability and everything. And we're suggesting to use structured concurrency. It's quite a simple class which allows you to execute different concurrent actions from the same scope, wait results, but it provides different kind of failure propagations, short-circuiting, like shutdown on failure, or just you do different several requests, but you need only one of them. Also, everything here is provided from a box. It's quite a simple API, and we're mostly waiting your feedback from this. Thank you.